Welcome to this video, Electrical Analogous Circuits to a Variable Mass System. My name is Benjamin Bacon, and in this lesson I will be putting the finishing touches on the information that I have given you in the previous lessons. One of the first challenges that you will encounter when implementing the electrical analog circuit is that the circuit is based upon the actual values of capacitors that can be acquired in the market. Historically, the electrical component market provided only values that are standardized, and so only certain values can be purchased. And it is similar to the situation that you have with resistance. And also, these standard capacitor values were generally less than 1 in magnitude. They were a fraction of 1 farad. Now there are ways around these two challenges. First of all, capacitors of any values between the standard values can be custom made if you are a maker of things, or you can have a manufacturer make custom values for you. And also, we have a new type of capacitor on the market today that is called the supercap. And these supercaps have values that are greater than 1. If we happen to be dealing with small-scale masses and forces in the mechanical system, and these are of the same scale as the capacitor values that we have available in the market, then the electrical circuit can be implemented directly from our mechanical model. Let's take a look at the table of capacitor value scales that we have to work with. We have capacitors that are around 1 to 10 farad. These are on the order of the scale 10 to 1 millifarad range. It's on the scale of 10 to the minus 3. We have the microfarad range on the scale of 10 to the minus 6. The nanofarad range that is on the scale of 10 to the minus 9, and the picofarad range that is on the scale of 10 to the minus 12. These are the common values. And with these common capacitor values, we can cover a wide range of mass values in the system model. This is more than 10 orders of magnitude wide, up to about 12 orders of magnitude. Now, if the electrical analog can be implemented directly from the mass values in the mechanical system, because it has small-scale masses and forces in the mechanical system, then an example will serve to show us how this is possible. Let's say that M1 and M2 have the value of 2 times 10 to the minus 3 kilograms, and M3, the varying mass, has 0 to 2 times 10 to the minus 3 kilograms magnitude. This can be implemented in the electrical system by a capacitor C1 and C2 having 2 millifarad value, and a differential variable capacitor C3 that can range from 0 to 2 millifarad in value. This is a direct implementation from mechanical to electrical. The magnitude of the resulting force and current that will happen in the simulation will be determined by the flow variable rates that occur, and according to the analog they will be equal. That is, the derivative of voltage with respect to time will equal the derivative of velocity with respect to time. Let us consider large-scale masses as forces as those that are on the order of 100 kilograms or more. Now, masses of this value are putting a strain on finding market available capacitors, because that is at the upper limit of the current supercap technology that is available. However, we can continue because the magnitudes in these mechanical systems can be scaled to fit within the capacitance value range that we can find easily. So let's take as an example setting a basis of 1 nanofarad being mapped to 100 kilograms. With this basis, there are enough capacitances to represent mechanical systems that have mass ranges from 100 kilograms to 100 times 10 to the 10 kilograms, or up to 100 times 10 to the 12 kilograms, or perhaps even more. And these can be modeled in an equivalent circuit using current values of capacitors. This scaling may work, but we cannot guarantee that the results from these scaled models will be accurate. That can only be determined from experience after you've used systems of this type, analogs that are scaled. Then you will eventually know from experience whether the accuracy from scaling is good or bad. In the previous lessons, only the basic circuit implementation was described in the diagrams that I showed you. That basic circuit implementation can be improved by the following means. We can apply op-amp circuits, and these op-amp circuits can be used to build what are called differentiators that can differentiate our output signal for us and give us the derivative values that we are seeking in analog fashion. We can also use integrated circuits, and these integrated circuits allow us to implement variable capacitors that can be controlled by digital inputs and give digital outputs. And then once we have acquired and added these digital components, we can use digital computer to control the simulations and to control the behavior of the circuit. We can also add digital meters. Digital meters can be voltmeters and current meters that take our measurements for us and give us our outputs in digital form. And through these digital outputs and inputs, we can add computer-based measurement systems. Computer-based measurement systems come in a variety of forms made by manufacturers that provide both computer forms of the devices and analog forms of the devices. So we can get our voltmeters as a computer-based system or as a device, our ammeters, as well as all of our other measurements can be taken by a computer that is designed to mimic the virtual form of these analog measurement devices. I am now going to start explaining the complete variable mass system equations. It turns out that the equations that I used in the diagrams in the previous lessons were not the complete variable mass system equations. In fact, these equations are so large that they are too big to fit in the space of the diagrams. Now, these equations that were given earlier work perfectly for the case of constant mass systems. However, we are not going to be dealing with constant mass systems here primarily, but with variable mass systems. And so, in that case, we will derive the complete variable mass system equations from the first principles. And the equations that this derivation starts from are an equation for a charge Q of t, which is equal to C of t and V of t, which are both varying with time. And this equivalent equation in the mechanical system is P of t, the momentum, which equals M of t times V of t. In general, the electrical analog Q of t is used to represent distance and not momentum. However, the analog equations are not normally used on this first principle level, and we only apply them after the first order equations for these two energy domains have been derived. The first order equations appear as thus. We take the derivative of charge, and that will equal C of t times the derivative of voltage with respect to time, plus V of t times the derivative of capacitance with respect to time. So we see that we have two terms, unlike the one-term version that we gave in the earlier lessons. And also in the mechanical domain, the derivative of momentum equals M of t times the derivative of velocity with respect to time, plus V of t times the derivative of mass with respect to time. Once again, we have two terms, and the one-to-one correspondence in these two equations and in these two energy domains continues to hold. So the complete variable mass system equations in first order are as appears in this table. The mechanical system has two equations, one for each rigid mass that appears in the mechanical system model. They are labeled by the subscripts 1 and 2. We have the similar situation in the electrical system equations. They have one equation for each capacitance that appears in the system model, and they are also labeled by the subscripts 1 and 2. So as you can see, there are in total two equations for each energy domain, and therefore the system is indeed becoming very complex. Now, when we take these equations to second order, and we will use the mechanical version of the system in the mechanical domain as our representative equation for this process, here's what we're going to get. The second derivative of the momentum with respect to time will result in the mass times the second derivative of velocity plus the derivative of velocity times the derivative of mass plus derivative of mass times the derivative of velocity plus the velocity times the second derivative of mass. And so we see that in this result we have a term that appears twice, derivative of velocity times the derivative of mass. We can combine these two terms and get our final result, which is something like a quadratic equation, where we have the mass times the second derivative of velocity plus 2 times the derivative of velocity times the derivative of mass plus velocity times the second derivative of mass. This is a quadratic form. The second order equations then result in the following in the mechanical system, there are two second-order equations, one for each rigid mass that appears in the system, and they both take the form of that quadratic second-order result that we discussed previously. Finally, the second derivative of momentum, which we have derived here, is equal to the derivative of force with respect to time in our mechanical energy domain. And then we also have the same result in the electrical system. So the analogy and the one-to-one correspondence holds up. And we see that the second derivative of charge with respect to time equals capacitance times the second derivative of voltage with respect to time plus 2 times the derivative of voltage with respect to time times the derivative of capacitance with respect to time whole plus the voltage times the second derivative of capacitance with respect to time. So this also is a quadratic form of the results, and we have two equations labeled by the subscripts 1 and 2 as we have in the mechanical energy domain. And this result, the second derivative of charge, equals the derivative of current with respect to time. Now this looks very complex, but it could be even worse. It may be that we may require a unique system of equations for the third mass, the fluid mass. As we have done now, we have included the effects of mass 3 into the equations for mass 1 and mass 2 with the variable mass terms. Hopefully this is enough, but if it is not, and we have to develop a unique system of equations for the third mass, that may take us directly into having to deal with computational fluid dynamics to develop this system of equations. And we will have 3 sets of equations instead of 2. So what is the purpose of all of this that we are doing here? The purpose of it all is that the system is very complex, as you can see mathematically. The theory behind this is very complex. And so we are developing here as many shortcuts as we can. Every shortcut that we can get makes the job of analyzing, developing, and designing easier. So what we are designing here is an experiment to answer the questions: how much of the complexity that we have in this theory can be left out, and we still get sufficient accuracy in the analogy and in the model when we compare it to the real-world systems? And a further question, will we get good accuracy in the models as first described in those diagrams that I showed you in the first lessons? Those had just modified first-order equations, and would that be enough? If it is, we are in good shape. So now we're going to have a discussion, video the person, about some of the errors that you may have thought you noticed in my previous lessons. One of those errors is that I omitted the additional terms in the equations that I gave to you for the analogs. And now you see that there was a reason for that omission, that there was a leading design that came to this purpose that we have derived at here, and that purpose is to find the maximum simplicity in the equations that we can. So did I do that intentionally? Maybe in my subconscious I did do that intentionally. Another error was that I made an incorrect statement of the dimension in a dimensional analysis for the current. I said that the current was Coulomb volt per second, but that was not correct. The current was in the dimension of Farad times volt per second. Again, that may have been something that my subconscious was doing to tell me, and perhaps you too, that the equations that we were using in the first order were not the complete equations, but were only half of the total result. On the other hand, my engineering sense may have been telling me that, well, go ahead and use these simple equations, because in the end, we're going to try to find the simplest representation of these complex equations that we can. So there was kind of a trade-off between my engineering sense and my subconscious as to how I should proceed. So a couple of errors did pop in there, but they happened to turn out to be errors that are predictive of where we are now. So the lesson that we have learned is that the system is so complex and the theory is so complex that the dimensions and an error in the dimensions really has no effect on the outcome of the experiments. The dimensions do not play a role in the experiment, and they only become important when we talk about specific subjects or in specific types of conversations. Otherwise, we would be best served to focus on the more important things, like the number of terms that need to be included in the theory and the equations in order to get accurate results. That is what we want to focus on. Why should we want to focus on that? Because in the end, we have a reason that will be served by reducing the complexity. So in that line, here are the instructions. Here's what we are doing this all for. We're going to start simple and set up the electrical system as described in the diagram. Then take the measurements, and these measurements are going to be accurate. If we model an accurate analog to the mechanical system, the numbers that we get will be the right numbers. So the numbers from the experiment will guide us. We will plug this data first into the simple equations, the ones that I gave you in the diagram that left out terms, and evaluate the results. Now, if it's necessary, we may, or even desired, we can substitute this same data from the measurements into the more complex equations and compare the results from the simple equations with that from the complex equations. And ultimately, we want to answer the question, is all that complexity that we developed in the theory necessary? Can some of it be left out? And if it can, then that is what we want to do. That is what we want to get to, because we want to put these equations ultimately into computers. And computers can handle a lot of complexity, but complexity does one thing to computers, and that is slow them down when they try to do those computations. But say we're designing a control system that will actually drive a mechanical propulsion system of the type that I designed, then we want that control system to be as fast as possible. It has to keep up with real-time data. And by simplifying the equation, simplifying the theory, we can allow the computer to be faster in its execution of the equations and computations that it has to do. So that is why all of this is worthwhile. So do the experiments in this way, simple and complex, and discover how much of the complexity can be avoided. Thank you for viewing this lesson, and Godspeed on your interstellar journeys.